introduce one of my colleagues, Radu Ion. He's been a researcher in the Institute of Artificial Intelligence at the Romanian Academy for more than 16 years, I think, with a short break. He comes with a lot of experience in the research, in the academia, but also in industry. He's an engineer, but he was very keen on understanding the data he works with. So I've always appreciated his interest in learning and understanding how language works. So today, Radu Ion will give a talk about deep learning experiments at RACAI.
Thank you very much, Dominika. Very nice introduction of me. Thank you for the invitation. I'm going to briefly present. I don't think I'll use the full hour. Okay, I think we're just on track now. Okay. Yes. Oops. Okay, excellent. That's okay. That was unexpected. No problem. I can. I have a solution. 1 minute. Okay, let's see that works. Okay, so I'm going to present some experiments I did for I think for the past year at the Research Institute for AI of the Romanian Academy. What I'm going to talk about are my own experiments, which is not to say that my colleagues haven't been using neural nets and doing NLP with them. I'm just going to talk about my own work. So, deep learning is a field which currently deals with machine learning using neural nets. And it started, well, bits and pieces were introduced some while back. For instance, this Crescentron, which performed like 3D object recognition in images. It was the first to use the max pooling algorithm to downsample a picture. So that's a concept that is used now in convolutional neural nets. But it was introduced a while back in this paper. Neural nets are around for a long time now. Even the backpropagation algorithm. What was not around was the computing power required to train neural nets with more parameters, hundreds of thousands or millions of parameters. But I think for the past decade, 10 years, the affordable computing resources really sparked this field. And nowadays we have CPUs with 8 cores are commonplace. We have GPUs on very cheap graphic cards. And we have, as well, we have libraries which enable everyone to train and evaluate a neural network, which is a good thing. on one part, but on the other hand, the field, at least the way I see it now, in the industry, but even in the research, reading various research papers, the deep learning is like a game of Lego. So people will try and mix different parts of neural nets, will try and see if they get good results, but with not very deep interest on what it means to get good results and why they are achieved or why they are not achieved. So that's one aspect. Another aspect is that the deep learning libraries have become very refined, and they shield users from problems which used to be used to occur that would hamper the results. For instance, the vanishing gradients or overfitting and providing learning rates. And there are all sorts of engineering bits that have to be done in order to make a neural network. And back probably, let's say 5 years ago, you would have to solve these problems yourself. And by solving them yourself, you would actually learn about how the forward propagation works, how the back propagation works, why the gradients vanish and you don't learn anything, how you overfit your training set if your neural net has millions of parameters but you only have like 1,000 training examples, and all sorts of these things. Now you'll have to work harder to see these problems. But in the end, we really don't know why they work the way they do. I'm sorry to disappoint you on the spot. I'm not going to solve this problem myself. But at least I'm looking at the architecture and try to match it to the problem I'm trying to solve. Deep learning at our institute. The first experiment I'm aware of, at least, began in 2013. Our colleague TB, which is standing right there. So he wrote a neural net that would do post tagging using the extended MSD post tag set, which has more than 700 labels. Previously, this problem was solved in a two-layer approach. So we had a reduced tag set with only around, say, 100 labels, and using afterwards a dictionary, we could map from the reduced tag set into the expanded tag set. But TB tried a neural net at the task of directly tagging with the expanded tag set. The network wasn't very deep. It only had a single hidden layer with a number of neurons, which was a hyperparameter. It could be tuned, and the output layer was a real value vector representation of a MSD. So each attribute was encoded in a vector. I'll show you exactly how. This neural net was trained to recognize the target MSD inside a window of 5 words around the target. And testing showed that this network was able to achieve like more than 98% accuracy on the extended tag set. I think even 98.4 with 130 neurons. So what that was the first, let's say, recognition that a neural net is able to learn better at the same time the standard hidden Markov models approach that we were using previously. And that was an encouraging experiment. Once again, some other experiments may have taken place if I don't know about them. What I'm going to present, I also try to upgrade my HTML, my hidden Markov model approach to post tagging, and tokenization, sentence splitting, post tagging, and lemmatization. The past year I was also trying to use neural nets to solve these problems once again, but with a special accent on Romanian. The first experiment I did was with sentence splitting, which can be framed as a sequence labeling task where the token that will split the sentence is appropriately labeled with a, let's say, with a sentence end label. And the other tokens are inside the sentence, so no sentence end and sentence end. You can see a training example here. I have annotated by hand, say probably around 50,000 tokens with sentence end markers. Took me around 2 months just to have a training set for this method. What goes into this very simple neural net? Okay, I'll explain the architecture. Okay, I don't know how to go back. So what goes in is a vector of different things. First of all, our new tokenizer will break the sentence into tokens using some tokens labels. We have abbreviations, we have numbers, we have words that are in are Romanian words, which are in a Romanian lexicon. We have multi-word expressions, foreign words, and end-of-line spaces, punctuation, and symbols. So the first part of the input vector is encoding on this vector. Then we are using the Python name function from Unicode, saying which are the Unicode name of each character in the input word. This list is split by spaces, and it follows a one hot word encoding of this set. Then we are using a one if the word is a lexicon, and also a one hot encoding of the possible word possible part of speech of the current word. And this word is appended by a word embedding vector for the target word, derived from the Corolla corpus. So this is what is taken by the neural net as the input vector. Then the architecture is a simple one. It's a simple bidirectional LSTM neural net, which has a output of it takes the input vector, it outputs a dense layer that will connect the state vector of the LSTM cell to position either in sentence or out of sentence softmax layer. So it's very simple. The thing here is that with respect to what I said earlier, that I tried to match the architecture with the problem at hand. Several more advanced architecture were tried as well. Like I've tried to stack like 2-3 layers. I've tried to do also using some other features that goes directly into the output layer, and all of these experiments told me that the actual results were worse than what I got with the simple structure architecture. This net has almost 1,100 parameters, which is not a lot with respect to the size of the training data I have. I have more than 100,000 samples, which I can train on. It's brief example on how you can build that simple network from the previous slide in Keras. It's a simple functional approach. You define your input vector as x, and then you add layers by calling the the layer name on your input vector or your intermediate layer. Then the last step, you'll have your activation function name. So it's really simple to develop that neural net. And I've trained that for only 10 epochs. It's very fast. It's one epoch took like 22 seconds. I was able to get a F measure of around 98, more than 98.5, which says that the sentence splitting problem is not that it's not that easy. I mean, it's not trivial. It cannot. I mean, there are cases where the punctuation is ambiguous. The end of sentence punctuation is ambiguous. So that was the sentence splitting neural net. It was followed by post-tagging neural net, which actually is a composition of two different nets. The first one will transform the input vector into a MSD encoding representation using also by LSTM cells, and the second one will use a feed-forward neural net to transform that into a softmax layer, which will say which MSD exactly is that learned representation. Well, I did that a while back. Now I realize that I can only use a single neural net to do this. I need to solve the same problem. I don't need two. But I'm reporting results as they exist now. Training and testing data was 1984, which is the same data that TB used in his neural net. So I think the results are comparable, even though we did not use the exact development and test sets, but the sampling was the same, 90% and 10%. 90% training and 10% testing. What is learned here? The encoding of an MSD label is the MSD label is actually formed by multiple attributes. The first one is the pos, is the part of speech of the label, and then multiple morphological attributes follow. This is a common noun. It's a feminine noun, singular in a direct accusative or nominative case, and not articulated. So if you do sets for each of these columns, you can create a one-hop encoding for this MSD. And this representation is learned by the first neural net, and then after the first neural net is trained, mapping from this learned vector into the actual MSD is realized by the second neural net. For the first architecture, the neural net that learns the MSD encoding, it's a simple bidirectional LSTM neural net. And again, I have to say this again. Even trying with stack layers, trying with the doing decoding, I haven't tried with attention yet. But still, the simplest architecture is the one getting me my best results. Which can say, well, this does not mean that this is the absolute best architecture available. In this case, probably it means that I do not have enough training data to make more complicated architecture work better. So that's one interpretation. The other interpretation is that there could be a even more complicated architecture that works better, but which I haven't found yet. But still, using the simplest architecture will give me my best results, and it will give me also a very fast training and testing loop. This neural net is minimizing the binary cross entropy between the encoding representation and the learn representation. So this is what is optimized by the first net. And after the first net is trained, its output is given to the second net, which will learn to map from that encoding vector to the actual MSD with a softmax layer on the output. So after this vector is learned by the first neural net, then the second neural net will learn to map from the encoding to the actual MSD. Well, comparing this to the previous experiment, this is the let's say the novel part, because the 2013 neural net was, if I remember correctly, was mapping the learned representation directly to the MSD by a let's say cosine vector. So the best one was mapped by cosine vector, whereas with this new one, we simply learn the new mapping automatically. Second neural net is a simple feed-forward network with a hidden layer. It has like 512 neurons, and the output is the size of the set of the MSD, 749 labels we have in that set, and it will learn it by doing softmax and a categorical loss entropy. Okay, so both neural nets were trained for 20 epochs. This one is kind of slower. I've tried it on a GPU. It works like in half of this time. So this is a case where let's say probably around 2 million parameters will actually train faster on a GPU. What has to be observed here is the development accuracy, which is 98.18%. So that taught me a very important lesson, is that compared to the 2013 neural net, this one is more complex. It has two nets. It has evidence from the both left and right contexts. Should be performing better, but apparently it does not. So I'm starting to think that it's unless you have a very good reason, you just have to use the simplest architecture for your problem. Unless you can explain exactly what you want to learn extra, that will make the difference. So far I'm not seeing any significant improvement from the 2013 baseline, so I haven't gone above that yet. Some of the difficult choices which the current neural net postagger is facing they are the same as the one that Virginia presented earlier. So we have problems with adjective versus participle. So the participle can have values that can fill in positions that are filled by adjectives. we have like the noun and adjective distinction, and then the adverb versus adjective. These are the most frequent problems. So what I'm already doing now, I'm writing features that are specific to Romanian now, just to solve these problems. So I'm looking at the sentence and I'm giving it hints if the word can be an adjective, or if a word it should be an adverb, or if to be is should be a main verb or a auxiliary verb. And the intent is to make these two neural nets and also others to work very well on Romanian. And my goal is to, at least for the post tagging, is to do better than 99% on the MSD post tag set. And also to add lemmatization and dependency parsing. Well, I'm already kind of a bit more over the deadline for this task, but I'll keep working at it. And when it's done, it will be open source and available for anyone. So that was about the text preprocessing. Our one final experiment I want to present to you is the PharmacoNer 2019 shared task. This task was about recognizing biomedical name entities in Spanish in a provided training set, provided corpus. The team was composed from me, my colleague Vasile, and my colleague Maria. We have submitted like 5 runs obtained from ensembling our RPCN net with a simple gazetteer approach. Our best run was scored at 84.98% of measure with the exact offset and label matches. The best run had F1 of 91%. That put us on the 14th place among the teams, among 22 teams, participating teams, and our best run, an ensemble run, was ranked 38 out of 75 submitted runs. The task was to recognize 4 labels, out of which 2 were very frequent and 2 were very infrequent. Probably the distribution combined was 80% versus 20%. And I think that our system won at for the normalizable label. Normalizables are concepts that are present in SNOMED-CT biomedical lexicon, and proteins are names of proteins. But I just want to present the neural net that was a part of this ensemble algorithm. So again, we see the recurrent LSTM cell that is used. Again, we have tried with more complex architectures, and the net result was that we should again use the simplest architecture, which provided the better results. And that was because in this case, because we only had like 3,800 training examples. So you don't construct a neural net which has like 4 million parameters for a 3,800 training set. The neural net used biomedical word embeddings, which were provided in some other paper for the Spanish domain. They were specifically trained on a biomedical corpus. And also use the SNOMED city lexicon as a gazetteer list. This is the picture of the neural net, RPCN neural net. This you'll have your by LSTM layer. You'll have your states coming from the left and the right. Here we are using the word embeddings externally provided, the ones that were trained on the biomedical corpus. We also added a neural net word embedding layer so that the words that are present in the training corpus are learned. And we simply add the two vectors to have evidence from both sources. We also use the post tag of the current word, and we embed its representation in a post tagging layer. We're using suffixes, affixes, prefixes, and suffixes, 5 characters for each word to be able to learn patterns in the naming of the chemical substances. Like I said, we are using, if available, we are using the gazetteer label for the current word. That one goes into the by LSTM layer, and also for better precision, it goes directly into the output layer. And we also have 2 different features here, some shape features, different uppercase, lowercase numbers in the naming of the entities, and some SNOMED city features. All this machine works by multiplying the left and right states, which goes into an attention layer and finally into the output layer. Like I said, these direct links go into output layer for a great improvement in precision of the network. And the performance is the baseline. The RPCN network had a recall of 76%. The baseline was based on the SNOMED city gazetteer. This proves that the network was able to learn like 5% of new entities, but its precision is not spectacular. So the final F score is below the combination. This one, the prior one, is the combination between the ensemble between the gazetteer method and the RPCN, choosing for overlapping entities, choosing from the baseline. RPCN alone was ranked like 47th out of 75 participating systems. Okay. So yeah, concluding remarks. It's like DNN are the easy way out to difficult classification problems, providing that you are invested into putting time and do the experiments and do the hyperparameter tuning. Currently, there is no way to say for definite which architecture is the best, and I think the research should go into this direction a lot. And then, if you wanna, at least if you have to experiment, you'll have to make sure that your training and testing loops are very fast. So use complex architecture only if you are sure that you need them. A personal experience is that the GPUs are effective only when you have to deal with large nets. Do not use it for small nets, it will only slow you down. And this is a work in progress. I'm still trying to see why the architecture I use is the best suited to my problem. Don't have an answer for that yet. Thank you.